Hello everyone, my name is Yishen Zheng. I am from National Sun Yat-sen University. My advisor is Longhao Hu. Today, the report topic I am talking about is hydrophobicity and hardness of polysilicon ceramic precursor integrated with fluoride nanofilm. This is the outline of my report. First, we will explain our motivation. The Earth consists of 17% water, so the marine traffic is obviously critical whether it is for transportation or strategy. During the voyage, ships are inevitably polluted by oil pollution or microorganisms in the ocean. It will enhance the ship's weight and ship's resistance. Therefore, the fuel and greenhouse gas emissions will increase, and the ship's speed will also drop. The picture shows biofueling on the ships. So, design a nanofilm to keep oil pollution or microorganisms from adhering to the ship's surface and protect it from corrosion. This extends the age limit of ships and reduce the frequency of maintenance. During the last century, several precursors have been developed and investigated. The picture shows some representative examples. In this study, polysilicon ceramic precursor is the main solution. Silicon-based polymers are outstanding materials for coating applications. These compounds have excellent properties, such as strong adhesion to most substrates, and high chemical, thermal, and UV resistance. Polysilicon ceramic precursor is one kind of silicon-based polymers. It can be further heat-treated to convert them to silicon-based ceramics. Polysilicon can be formed by polymer processing techniques because of its liquid properties, such as casting and pressing. And dip coating, spin coating, and spread coating methods are the most frequently used to prepare coating of silicon-based polymers. In this report, we use dip coating and spin coating. AF340 is one kind of fluoride. It is able to lower the pyrolytic and cross-linking temperature of the polysilicon. By adding this additive, the hydrophobicity, hardness, and corrosion resistance of the coating layer can be improved. Silicon wafer is used as a substrate to test contact angle and hardness. First, pure polysilicon and different concentrations of polysilicon with AF340 is spin coated on the silicon wafer, and then put the coated wafer on the heating plate at 150 degrees Celsius for 10 minutes. Duplicate step 1 and step 2 5 times to form an evener coating layer. The next step is putting the coated wafer in a vacuum oven for shaping for 1.5 hours. And final step is pyrolyzing in a tubular furnace under inner gas for 3 to 7 hours. Copper foam is used as the substrate to test anti-corrosions. We use copper rod as the electrode to connect with copper foam, and then dip coating in the polysilicon for 2 minutes. Ultimately, the coated copper foam pyrolyzed at 200 to 500 degrees Celsius to form a PDC coating layer. We used an electrochemical analyzer to analyze the corrosion resistance of the coating layer. And the electrochemical analyzer consists of working electrode, reference electrode, and counter electrode. The electrolytic solution is 0.5 m sulfuric acid. This page shows all the parameters of the experiment. The pyrolytic temperatures are 200 to 500 degrees Celsius. And the concentrations of AF340 are respectively 0, 1, 5, and 10%. The picture shows the thickness of the coating layer is 1.42 micrometer. The pyrolytic temperature is 200 degrees Celsius, and the concentration is 10%. We use the cell drop method to measure contact angle, and the picture on the right shows the results of color contact angle. We can see that the wafer coated by pure polysilicon and polarized in 500 degrees Celsius has the better hydrophobicity. Compared to the uncoated wafer, the contact angle increased from 71.4 degree to 118.6 degree. Under the pyrolytic temperature of 200 degrees Celsius, the contact angle with 10% additive of polysilicon can achieve 111.7 degree. Besides, the effect of F340 is more obviously at the pyrolytic temperature of 200 and 300 degrees. This page shows the hardness and the reduced modules of the coating layer. As shown in the left picture, the wafer coated by pure polysilicon and polarized in 500 degrees Celsius has the better hardness, and the hardness of the coating layers are all higher than the aluminum. And the better reduced modules occurs in the pyrolytic temperature of 400 degrees Celsius and coated by the pure polysilicon. According to the left picture, the trait of the hardness is similar to the hydrophobicity. When adding 10% F340 and polarizing in 200 and 300 degrees Celsius, the hardness and the hydrophobicity are all improved. On the other hand, the pyrolytic temperature of 400 and 500 degrees Celsius doesn't have the effect. According to the definition of contact angle, the coating layers are all hydrophobicity. This page shows the results of Tafel curve. According to the left picture, we can see that S340 can improve the corrosion resistance because the red curve has higher potential applied than the gray one. And the picture on the right shows the PTC coating layer has corrosion resistance. The red curve has the highest potential applied in this experiment. And the pyrolytic temperature is 200 degrees Celsius. Concentrations of F340 is 10%. The blue curve has the lowest potential applied in all the parameters, which is polarizing at 400 degrees Celsius and coated by pure polysilicon. But they all have higher potential applied than the black curve, which represent the uncoated copper form. The wafer coated by pure polysilicon and polarized in 500 degrees Celsius has the better hydrophobicity and hardness. Under the pyrolytic temperature of 200 degrees Celsius, the contact angle with 10% additive of polysilicon can achieve 111.7. The copper form implanted in the 10% of additive solution and polarized at 200 degrees Celsius has the highest corrosion resistance. With the additive, the pyrolytic temperature can be reduced from 500 to 200 degrees Celsius, and the hydrophobicity is similar. It can effectively reduce the pyrolytic process time. The ceramic coating layer we made is multifunctional. It has hydrophobicity, corrosion resistance, and higher hardness than aluminum. In the future, we will try to add other materials like graphene to increase the hydrophobicity, and discuss the surface roughness and the thermal conduction of the coating layer. This is our reference. Thanks for your listening.